You doing okay this morning? Yeah.
Alright, so I haven't made out an exam yet, but it's going to be right around 40 questions, 40 to 45. It'll come from all 4 tests. It'll be similar in its combination of, conceptual to calculation type questions. In fact, I think there are probably more conceptual questions than calculation. Okay? We can go through the 4 exams. If y'all have particular questions, we can answer them. But as I said, I'm going to just focus on those 4 exams. Because if there's material that's not in here, it's not going to be on the final exam. Everybody's clear on what I mean by that? I talked about this yesterday in class. Everybody's clear? Okay.
Do y'all have particular questions? We can just start with exam 1. Any particular questions from exam 1? Ideas that are difficult for you that we can explore further? Number 6, yeah. Okay, so I have a configuration of 2 charges shown, and I want to know where I put a 3rd charge so that the net force on that 3rd charge is 0. And you need to ask yourself, is it going to be a positive or a negative charge? So I just sort of start picking out the different points, because I know it's either going to be here, either here, or here, or here, or here, or here. Either at the center point, or to the left or right of the center point, or to the left or right of the charges. And so let's just start over on the far left. So let's imagine that I put a positive charge there. It's going to be attracted to that -2 charge, and then it's also going to be repelled from that -3 charge. Now it turns out that's going to be the answer, that's the place right there. But let's look at the other places and see why those aren't the answers. So right here, for example, if I put a positive charge here, it would be attracted to the -2 coulomb charge, and it would be repelled from the +3 coulomb charge. Okay? So now let's look over here on the far right. Let's say if I put a positive charge here, it's going to be repelled from that +3 coulomb charge, and it's going to be attracted to the -2 coulomb charge. Because it's so much closer to this bigger charge, though, this force is going to be a lot bigger than this force, because it's so much closer to the bigger charge. So what we need to do is get farther away from the bigger charge and closer to the smaller charge. Now those are all for positive charges, but if we looked at negative charges, if I put a negative charge there, it would be repelled from the -2 coulomb charge, and it would be attracted to the +3 coulomb charge. So even if I had a negative charge there, the forces would just switch places, and it would still have a net 0 charge. So how could I take this and change it up, right? Well, here I asked about the forces. I could also ask, what is the electric field, right? And that would be a very similar question. Where is the electric field due to these charges going to be equal to 0? What would be the answer for where is the electric field 0? Which of those positions? To the left of the -2, to the left of the center point, at the center point? Where would the electric field be 0? It'd be the same answer, right? Because the electric field is the point where a positive charge feels a force. So the electric field would also be equal to 0 in this region, off to the left of the -2 coulomb charge. You can also ask where the potential is 0. That's slightly different. We have other problems that are similar to that, asking where the potential is 0. All right? Good question. What else? Yeah. Number 8. Like, do you want me to do it really fast? Okay. All right. Listen, you're going to have questions like this. You're going to have to deal with vectors in 2D. Make sure that you can do this whole string of questions from 7 all the way down to 9, because you will have questions calculating the potential. Yeah, you want to start with 7? That's probably a good idea. And let's not do it real quick. Let's do it normal pace. Okay? So what is the magnitude of the electric field at point A? So at point A, I first imagine that there's a positive test charge there, and then I ask myself, what is the direction of the force that that positive test charge feels? And the positive test charge feels an attractive force to that -8 coulomb, and a repulsive force from the +2 coulomb. I'll call this E1, I'll call this E2. And then we need to calculate the magnitude of E1 and E2. So E1 is equal to KQ over R. That's 9 times 10 to the ninth. Q is 2 times 10 to the minus 9. And then R is 2 meters. Excuse me, it's not R, it's R squared. 2 meters squared. I get some things that cancel out here. These cancel here. And then one of the 2's on the bottom cancels with the 2 on the top. 2 over 4. So that's going to be 9 over 2. That's equal to 4.5. And then if I want to do E2, it's very similar. I have 9 times 10 to the ninth, that's K. Q is 8 times 10 to the minus 9. Remember, I don't put the negative sign there. Only when I'm calculating the potential do I put the negative sign in. The negative is implied when I put in the vector, when I draw the vector. Divided by R squared, which is going to be 4 squared. That goes away with that. This and that cancel out and leaves me a 2 in the bottom. So that's equal to 4.5. So both of these vectors are the same magnitude, but if I want to know the net magnitude, it's going to be the square root of 4.5 squared plus 4.5 squared. I know it can't be that or that. I think it's C. Pretty sure it's C, right? Yeah. Okay. I could change this to, it's a very similar question to ask you what is the force. In fact, no, that's how I've taken this question. And I've taken this question and I put another charge right here and I ask what is the force on that charge. And it's the same problem, practically, except the only difference is that when I'm calculating the force vectors, I'm doing KQQ over R squared. So it's practically the same question, it's just asking the force instead of the electric field. But it works out exactly the same way. Okay? Like instead of having this question, you're going to have 3 charges, and I ask you what is the force on one of those 3 charges. And I have them arranged so that you don't have to, the vectors don't get funky. The component vectors are both on the x and y axes. Same procedure that you do. It's just when you calculate F1 and F2, you have to use Coulomb's law. So KQQ over R squared. Okay? The 8. Oh, right here? Okay, no, it's going to be kept positive. She asked, when I put this here, should I make 8 positive or negative? Remember, whenever you're dealing with vectors, you don't put the negatives when you're calculating the magnitudes of those vectors. Because the signs of these charges come into play when you draw the vectors. If this would have been a positive charge, I would have drawn the vector in the opposite direction. Whenever you're dealing with vectors, that's forces and fields, you don't include the negative signs. It's only when you're dealing with scalars, that's potential. All right? Forces and fields, leave the negatives off. They're implied when you draw the vectors. But when you're dealing with scalar quantities, which is really just potential, and potential energy, then you leave the signs out, or you do include the signs. Vectors, no signs. Scalars, yes signs. The signs have a different meaning. They don't mean direction. Let's look at these others, because you'll have, depending on which class you're in, you'll have sort of a combination of one or more of these. And I've been very careful to make the exams similar in difficulty, okay? That if I choose a really difficult question for one class, that I choose a similarly difficult question for the other class. But they're not going to be identical. So I'm sorry, I'd love to clump y'all all into the same room, but that's just not practical. All right, what is the direction of the electric field at point A? Oh, so define the direction. Oh, this is easy, right? Because the 2 components are the same magnitude, so it has to be 45 degrees. I don't even need to look at the others. It has to be 45. But if I wanted to determine that, well, first, if they weren't the same, my resultant vector is going to be here. To find this angle, theta, I would say that the tangent of theta is equal to the E1 over E2. So theta is the inverse tan of 4.5 over 4.5. Inverse tan of 1, but that's 45 degrees. And notice that it is above the negative x-axis, which jives with how I've drawn it over here, that this, my coordinate system, is right there, and so that vector is above the negative x-axis. Now potential, how do you find the potential? KQ over R business, scalar or vector quantity potential? That's a scalar. So the big thing here where you want to not mess up is make sure you do get those signs in, because you'll find both options in the answers. Here I only have two charges, so it's going to be KQ over R, KQ over R. Let me just erase all this. Uh, 9 times 10 to the 9th. Q is 8 times 10 to the minus 9. Look, I put in that negative sign, divided by R, which is 4, plus 9 times 10 to the 9th, 2 times 10 to the minus 9, divided by R, which is 2. You do some cancellations. I try to give you cancellations, it just makes your math easier. So that's negative 18 plus 9, so negative 9 volts. Notice if you wouldn't have put the negative in, you would have gotten, you would have gotten 27, and then you would have said, oh, where's 27? All right? It looks like I didn't put that option in. In number 10, if you wanted to find the force that it experienced, you could go back and do the whole thing with Coulomb's law, or you could just say F is equal to QE. And if you do that, F is equal to QE, then you take your answer that you found over here, 6.4 newtons per coulomb, and then multiply it by the charge, which is 3 coulombs, and then that gives you the force. That's 19.2, 19 newtons. That's a good series of questions. You'll see a couple or 3 questions like those for certain. You'll see at least 2, maybe 3. Okay? Any particular questions on this? Mm-hmm. Okay, so 25 is paired up with 24. Let me just tell you, protons roll downhill, electrons roll uphill, right? Electrons are funky because of the negative charge, and so they move uphill instead of going downhill. They move from low potential to high potential. But if I have a proton, like I have here, a proton, it moves like normal downhill. So it moves from high to low potential. So here, if I have an electron that I want to know its speed, it's just like we did last semester. You're changing potential energy into kinetic energy. Remember that potential is energy per charge. That was sort of our basic underlying principle for potential. And so energy then is equal to Q times V. So if I have a charge that changes its potential, it gains energy. That's equal to the charge times the potential. And so I can further say that that energy, QV, is equal to 1/2 mv squared. Let me rewrite that V as a script V, because that's our speed, right? That's our kinetic energy. Our potential energy is equal to our kinetic energy. And then I solve for V. I solve for little v. It's going to be 2qv over m square root of that. I think these equations, they're on your equation sheet. Like this is on your equation sheet in some form. I think it's V is E over Q. This is not. This is just kinetic energy. But you will need to know this. You need to know your kinetic energy. So that's equal to, what is that? The square root of 2. This is an electron. Remember, you know the charge of an electron. 1.6 times 10 to the minus 19 times V. I'm going from line A to C, that's going from 10 to 30. So I have 30 minus 10. So that's my delta V. Delta V here is equal to 20 volts. Divided by the mass, what is this, an electron? 9.11 times 10 to the minus 31 kilograms. And then that is, I don't know what that is. You don't know what the answer is? B? D? Again, a good question. It's an important idea that when charges move through a potential difference, that they gain energy. It's important for biological applications too, because you have charges that move back and forth between the cell membrane, and they do that because there's a potential difference. Good question. All right.
I just like calculated it and it gives me like 2.7 times 10 to the 23. I don't, maybe I plugged in the
Yeah, I think that you did. Can I see? Be careful with your calculator. Yeah, because your square root, you need another set of parentheses in here, right? That goes around here and all the way to the end, because your leave is 9.11 outside of the square root. All right, what else, folks? Yeah, Savannah?
If you do number 7,
I hate electric fields. I mean, I don't hate them, but I don't know why I put this question, because that's not my favorite topic. Is it your favorite topic? Electric fields? It's probably the hardest topic we've had all semester. Number 7? Okay, so you'll certainly see some circuits. There are several for me to pick from, for capacitors and for resistors. What is the voltage across C1? So, if I simplify this circuit a little bit, I got a capacitor C, and then I have a capacitor up here that's 2C, because combining these two, they just add up to 2C. And then I have 12 volts. Now remember, big capacitor, small voltage. Small capacitor, big voltage. That comes from this. Q is equal to CV. If V goes up, or rather if C is small, V is big. Because for a given capacitor, they'll have the same charge when they're in series. So these two capacitors have exactly the same charge. So the smaller capacitor will have the bigger voltage, and the bigger capacitor will have the smaller voltage. You know, later you can put in numbers here, but it's easier to think about this conceptually. Big capacitor, small voltage, small capacitor, big voltage. And this voltage is going to be half this voltage, because the capacitor is twice as big. And so I need two numbers that add up to equal to 12, one of which is twice the other number. And that's going to be 8 and 4, right? 8 is twice 4. So I know that these two voltages have to be either 8 or 4, and then I need to assign which one. So I get 4 volts here, big capacitor, small voltage, 8 volts here, small capacitor, big voltage. Then it asks about C1, and so C1 is, well, it's 8 volts. These, by the way, are 4 volts.
Okay, so like for number 6, when you do it, and you're like assigning the voltages, the first capacitor that you get to has the same voltage, and then the other two has the same voltage as how come it's different for
Oh, because number 6, you say? Because this circuit simplifies to two capacitors in series that are identical. I have a 4 microfarad and a 4 microfarad, because these two are 2 microfarads, and it combines with that to give me 4. And so these are both going to have 6 volts and 6 volts. Your circuits will be similar in difficulty, and they'll also be similarly simple in that the numbers work. They're not simple, but the numbers work out simply for the most part. Sometimes you might encounter some fractions. Rebecca? You're right. And that's another good idea to keep in mind, that for resistors, for resistors in series, this is all for in series, if R is big, V is big. And the reason is that they both have the same current, right? Resistors in series have the same current. Capacitors in series have the same charge. If R is small, V is small. We'll probably see that in another circuit soon. So it's similar but opposite. You will see circuits. You'll see both capacitor and resistor circuits. In fact, I can look at all these tests. As I told you, I actually wound up pulling about 70 questions. I haven't proportioned them out to the different classes. But, so, I mean, I could throw a rock at any one question. Most likely it's going to be in one of your exams. Know them all. What else? Yeah. Okay, so listen, there was the way I wanted you to do it, and then there was the way that most people did it. Okay? The way I wanted to do it is the way you do it in lab, where you think, oh, this is I versus V. That's like the equation of a line, y equals mx. And I know that I is equal to 1 over r times V, and so the slope must be 1 over r. Like, that's really what I wanted you to do. So, and then you find the slope. You don't need to write that down, because I'm going to show you a much easier way, which is the way that most of y'all did it. The slope is rise over run. It's a half. So my slope is equal to 1/2, so r is equal to 2. Most of y'all said, well, V is equal to IR. I want to know what is R. It's V over I. And then you just picked a point, like you picked this point. V is 15. I is 7.5, so it's 15 over 7.5, which is 2. That's how most of you did it. That's probably how you did it too. And that's okay. I mean, that doesn't matter because it's a linear plot. And so any point that you take off this plot will give you the same answer. So that I'm not upset about that. That's okay. That's the easier way to think about it. Okay? This exam. Exam 2? All right, any exam? Savannah?
For exam 3, can you do one?
Mm-hmm. So you want to go to your equation sheet. I never memorize these. I'm not sure if y'all do or not. But we're looking here for the magnetic field at the center of a ring. That's going to be this one, the N mu naught I over 2R. I know that it's that one because it has that value N in it, and when I have a coil of wire, it often has multiple turns. So as opposed to this one, which is the magnetic field due to a long straight wire, the magnetic field off to the side of a long straight wire. So here I'm looking at this, N mu naught I over 2R. So B is equal to N mu naught I over 2R. Looks like N is equal to 1 here. Mu naught is 4 pi times 10 to the minus 7. I here is 2 amps. Over 2 times the radius, making sure that we keep it in SI units, so it's 0.1 meters. All right, so we can cancel this and this. So it's going to be 0.4 pi, or let's see, that's 12, like 1.2 times 10 to the minus 7, or 1.3 times 10 to the minus 7, which is going to be our 13 microtesla. 13 times 10 to the minus 6. So this one, which you could see something like this, is really just knowing what the equation is and then being able to solve it. You'll need to be able to, or make sure you get your SI units right. Yeah, Ben?
Isn't the denominator supposed to be 2 pi on it?
No, that's for some distance from a long straight wire. So if we go back to our equations, I have two equations here. You see this? Okay. Yeah. I have this one, which is the magnetic field due to a long straight wire. So if I have a wire, what's the magnetic field right here? And that has the 2 pi r. But then I have this one that looks really similar, U naught I over 2r. But it's different in that it has this N. And anytime I have a coil of wire, I often have multiple turns. And that problem did not.
Can you work number 10, which is the right-hand rule part?
Sure. I have several right-hand rule questions. And you have several that are like this, where I don't draw a figure. You have some where I do draw a figure, but you have several like this where I don't draw a figure, and it's helpful if you draw the figure yourself, okay? So I have an electron that's moving in the positive x direction. And first of all, I just want to make a big fuss about this being an electron, because often students will work through the problem, and they recognize it as an electron at the beginning, but by the time they get to the end, they forgot what they're supposed to do. So just make a big fuss. I don't know, pinch yourself or do whatever you need to do. So my velocity is in the positive x direction. My magnetic field is in the positive z direction. So that's B. And then I want to find out my force. Well, B is in this direction. B is like that. And so my force would be down, except it's an electron, so it's going to be up. And that's in the positive y direction. Oh, look, I don't even need to do anything. The answer is going to be B, right? Because my right-hand rule says it's in the y direction. And then you can double check that and just do the QVB, F equal QVB, to make sure that that's right. That is right, isn't it? It's B? Yeah.
So negative is the direction is into the page, not the-
Right. So on your coordinate system, this is positive z, and this is negative z. And then x and y, of course. X, right, is positive, left is negative. Because the world is not like that. You know that. All the, I say there. Anybody else? Are we the only ones? Ben, Ben. Okay.
I think it's number 16.
Okay. Yeah, this is a very similar one, but a good question. Like I said, the ones that I pulled there, you'll see one of these like this tomorrow, where you have to. It's helpful if you draw the figure. First of all, it's a proton. That's good. The velocity vector is in the negative x direction, and the magnetic field is in the positive y direction. So V is in this direction. My magnetic field is up, and so the force is into the page. And so I know that's either plus or minus z. Which is it into the page? It's minus z, so D is the right answer. Okay, yeah, Rebecca.
Okay, for 121, is there any rule, like, so you can know what, like, index of refraction the incident beam will go through? Or no?
What I always do is I draw a picture, and it says the light travels from glass to air. So then I'll say, this is glass, this is air, and the light is traveling in this way. And then I draw in my index of refraction, so I say this is 1.5, and then this is 1, and then my incident angle is 30 degrees. And then once I get that picture drawn, it makes a lot more sense to me. When I see just the text and I don't see a picture, it doesn't fit with me very well. So then, what is my N1 in this case? Well, the N1 is 1.5. Or at least 1.5 goes with the 30 degrees. So 1.5 sine of 30 equals 1 sine of theta. And then you solve for theta. Remember, if you get theta to be an error in your calculator, you might want to go back and just think about, is this total internal reflection? Because that might be the case if you exceeded the critical angle. In this case, yeah, you could get total internal reflection here if you exceed the critical angle. If that angle gets too big, it'll just reflect back and won't refract. Well, I mean, let's figure out what is the critical angle here. So I say 1.5 sine of theta, where this is going to be theta c. My critical angle is equal to 1 sine of 90. All right, that is my critical angle by definition. That's the point where the light is no longer refracting. Instead, it's coming back into the medium. And then I'd solve for that. It would be the inverse sine of 1 over 1.5. So it's 42 degrees. So theta c, it's equal to 42 degrees. For this scenario. So if this light ray goes at 42 degrees, it's going to refract in this way. That is, it's not actually going to leave the glass. It'll stay inside the glass. And if it's more than 42, it's not going to even go there. It'll just reflect back upon itself. Or not upon itself, but it'll reflect like by the law of reflection. 23? Is that okay, Garrett? Okay, so I always forget. Is the core the high index or the cladding the high index? The core is. And then I remember, well, a fiber optic cable is just glass inside of air. And so glass has a higher index than air. So the core has to have the higher index. And so the one that is the core is the flint glass, and the one that's the cladding is the crown glass. So B is the right answer here. Because optical fibers, they're not actually just a core. They have to have something that protects them, and that's the cladding. So they have the core, which in this case is flint glass, or whatever, it's usually plastic actually. But they create the core, and then they surround it by some semi-transparent material, which has a higher index of, a lower index of refraction.
Backtrack back to 21. I keep getting into the wrong thing when it comes to that. You said it was 42, wasn't it?
Mm-hmm.
I keep getting 8.5.
Y'all get 41.8. Y'all get that too?
The one for 21 should be 1.5 sine 30 equals 1 sine theta. That is different.
I'm not understanding.
You make
Sorry.
it, you work through 21 and the answer is 49A for 21.
Right.
And then you put it somebody else out there 20, and you went up to the top of the page and you're like, if we wanted to find the critical angle, this is how we work it, and then you wrote it up there.
Oh yeah, okay.
So it's a different problem.
So Ben, you've done this problem, right?
Yeah.
Yeah, and the answer to this is 49 or whatever you said. But yeah, I did a different problem over here. I asked, what is the angle that we get total internal reflection? No, it was separate calculation. All right. Is that clear?
Yeah.
So you did that first one right.
Yeah, misunderstood.
Okay. What else? Y'all asking great questions. Yeah, 22. Okay, so I have light traveling through some material with an index of refraction. What is the speed that light travels? So the speed is equal to c divided by n, and that's going to be 3 times 10 to the 8th divided by 1.5, which is 2 times 10 to the 8th. So when it's in this material, it travels a little slower than when it's in just a vacuum or in air. I want to know the time to travel this distance. Well, time, remember, distance is velocity times time. Our velocity is distance over time, however you want to remember that. So time then is distance over velocity, or speed, which is going to be 0.6 divided by 2 times 10 to the 8th. There's a 3 in there, so it looks like it has to be B. 3 nanoseconds. And I say that just because 6 over 2 is equal to 3, so I know my answer has to have a 3 in it. Yeah.
Do we just assume it's traveling in light unless you state otherwise in the problem? It's like, I don't know. I see.
Okay.
C is probably.
Yes, C is always right there. Okay. Other questions, other tests? We can go to others if you want to skip around. Savannah?
One more thing also find equations that the current
Like which one? Oh, the multi-loop circuits? Yeah, because you're going to have one. Both classes will have one. Let's see. Number 3? On exam 3? So first the equations, and I just go through, I pick the first one, and I look at the first number, it's 3, and so that tells me that I'm right here, and I'm going in this direction. Because to have a positive 3, it means I'm going from low to high. So I get 3 minus 2I1, that's okay, because I'm going with the current, and it is current I1, plus 5, that's okay, because I'm going from low to high, from the little to the big side of the battery, minus 6I1. That has a couple issues. First, it should be plus 6I, and it should be I2, not I1. So that one's not correct. The next one, 5 minus 6I2. All right, so I'm starting right here and going in this direction. And already I encounter a problem. What's my problem? It should be positive 6I2. Right, so let's just stop right there. This next one is minus 6. So that means if it's minus 6, I'm starting here and going in this direction. Remember, for batteries, the direction of the current doesn't matter. All that matters is the direction that you're traveling across the battery. So 6 plus 2I1. Okay, that's okay. I1 is the current I'm using, and I'm going against the current, so it's positive potential. Minus 3. Okay, that's okay, because I'm going from big to little, high to low potential, and then that's the end. So that's my answer. Let's just check my junction rule. At a junction, here, I have I1 and I2 going in, and that's equal to I3 going out. So D is not right, and then E is not right either for whatever reason. 3 minus 2I1 is because of the I3 right here. There shouldn't be an I3. That should go away. So you'll have a question like that. Both classes will have a question with the circuit and finding the right equation. And then you'll also have a question where you have to find the current. And it'll be made easier from what we had, say, in our workbook, where you had to solve a system of equations. And there are two ways to do that. You can do it like this, where I give you one of the currents, or I can make the circuit easier where you have a loop like this, for example, where there's no resistor in a portion of the loop. Like if you wanted to find I2 right here, that would be fairly straightforward. I could just take this loop and say 5 plus 6I2 minus 6 equals 0. And then I could solve that for I2, and you'd get 0.17. If I wanted another way to do it is I can give you I2, and then you have to solve for I3, in which case you can write the equation for the upper loop here and solve for I3. Let me write this equation. I'm going to start right here, and I'll go in this direction. I have 3 minus 2I1 plus 5 plus 6I2. That's all equal to 0, but I know I2, so I plug in I2 right here, and I get, what's that, 8 minus 2I1 plus 6 times 0.17. That's equal to 1. That's equal to 0, and so I1 is equal to 4.5. Okay? How do I get to I3? Oh, yeah, so I need to know I3, don't I? Okay, so if I wanted to know I3, yeah, 4.5 is not the right answer. I'm sorry, there was another step here. Once I know I1, then I can apply my junction rule. I1 plus I2 equals I3. Then I would say 4.5 plus 0.17, and that's equal to 4.67, or 4.7. Sorry about that. Okay. You will have multi-loops on there. Both types of problems where you have to find the equation, and then also where you have to find the unknown. What else? No, that's some great questions. Practically all of these are on the test. All the questions that you have, I think. What else? Anything else? Is that all? Yeah, great.
Number 19 from our last one.
Yeah. Okay, so I have two ways that travel. The important thing here is the path length difference and the wavelength. And then how many wavelengths make up that path length difference? So the path difference here is 2 meters. Path length difference is 10 minus 8, and that's equal to 2 meters. But the wavelength is equal to 3 meters. So if my path length difference is an integer number of wavelengths, that means I get constructive interference. So if my path length difference was 3, or 6, or 9, or 12, that would be constructive interference. If my path length difference was a half integer value, so if it was, 1.5, 4.5, 3 times 2.5, what's that, 6, 7.5. If it was that many wavelengths, that would be destructive interference. So constructive would be 3, 6, 9, 12. Destructive would be 1.5, that's a half wavelength difference. 4.5, that's 1.5 wavelengths. 7.5, that's 2.5 wavelengths, and on and on. But here I don't have any of those. I have 2 meters, and so it's going to be neither total nor neither total constructive nor total destructive interference will occur. Notice if you take the path length difference and divide it by the wavelength, this will equal a whole number here. If you do it here, it will equal something over 2. Isn't that right? 0.5 over 3, 4.5 over 3. Yeah, it'll be something divided by 2. Okay? They're going to be one of those first couple of options. So you'll be able to just say, well, 2 wavelengths is 3, 6, 9. It's not going to be like way out at some far distance. You understand what I'm saying? It'll be one of those first couple of options. Yeah, Rebecca? Right. No new questions from OpenStax, but only questions like that were from OpenStax on the test. Is that all? Susie?
For sound can see what was this, and for this intensity is modulated.
Right. Power per area. All right, people. Thanks for coming out so early. I got most of you.